Part 4 of Unit 7 is about real gases, effusion, and diffusion. Last video you learned about the ideal gas law and ideal gases. Unfortunately, real gases aren't ideal. Ideal gases don't actually exist. Real gases do have volume, they do experience intermolecular forces, and they do not have perfectly elastic collisions. When gas molecules collide, they do lose energy. Real gases that are most likely to behave like ideal gases are gases that are made of small, nonpolar molecules like hydrogen or helium that are at a high temperature and low pressure. That's the important part to remember. High temperature and low pressure, less than 1 atmosphere, are going to behave most like ideal gases. The further you deviate from the ideal gas behavior, when you get large polar molecules that are at low temperature and high pressure, those are not going to behave like ideal gases. So the ideal gas law could not be applied to them very easily. We have an equation that adjusts for non-ideal behavior in gases, and I really only bring it up because it's on the AP test equation sheet. I don't believe that I've seen it actually used on the AP test. Granted, I've only, looked at about 20 years of the AP test, not all of them, but I could be wrong, but I don't recall seeing this equation. Regardless, it's really rare, but it's called the van der Waals equation, and it looks like this. So it's the ideal gas law with corrected pressure and volume terms to correct for non-ideal behavior in gases. P, V, N, and T, those still mean the same thing as in the ideal gas law. The new terms are A and B. A and B are factors that are determined experimentally. They're unique for each gas. Hydrogen has a different value for A and B than helium does, and they should be given to you in any question that asks you to use the van der Waals equation. Now remember, this is rare. When you're doing problems that have you dealing with gases and maybe equations with gases, you're going to assume ideal behavior unless otherwise told. So you're going to use PV equals nRT unless you're told otherwise. All right, let's talk about the movement of gases. Diffusion is the movement and mixing of gases, and you need to know that smaller and lighter molecules diffuse faster because they're going to have more energy. They're going to be able to move faster. So when somebody in the back of the room opens up a container and starts munching on a stinky onion, eventually everybody in the room is going to smell that. That's because the onion scent particles are diffusing throughout the room. They're mixing with the air and gradually moving across the room. Effusion is what occurs when gas molecules move through a tiny opening into a vacuum. There's a picture of it down here. So this one gas molecule has effused through the hole in the middle of this container. The relative rate of effusion for two gases at the same temperature can be calculated using Graham's law of effusion. The equation for Graham's law is R1 over R2. That's for relative rate, and that's equal to the square root of capital M2 over capital M1. Capital M stands for molar mass of the different gases. So if we know the rate and molar mass of one gas, we can solve for either the rate or molar mass of another gas. We'll do an example on the next page. The important thing to remember is that they're flipped. 1 over 2 on the rate side and 2 over 1 on the molar mass side. So in our example, the effusion rate of an unknown gas is measured to be 24 milliliters per minute. Under the same conditions, pure methane, CH4, is measured at 47.8 milliliters per minute. What is the molar mass of the unknown gas? The first thing we need to do is designate one of the gases, methane or the unknown, as 1 or 2. We're going to call this unknown 1 and methane 2. So let's write our equation. Alright, they've told us the rate of gas 1, so we'll put 24 over the rate for methane, which they told us was measured at 47.8 milliliters per minute. Now, gas 1 is an unknown. We don't know its molar mass, so we'll just leave this as M1 down here. But methane, CH4, we can add up its molar mass. It's 16 grams per mole. So we'd be solving for M1, this term down here. So to do that, we would square both sides of the equation. So I'm going to take this one to the top of the page, so that we end up with, we simplify this term and square it, we get 0.25 is equal to 16 over x. Because when you square a square root, it's just that normal term. So then you solve that, x ends up being equal to 64. And remember, we were solving for molar mass, so the units are grams per mole. Sorry to kind of go all over on that one. Your question for this section: under certain conditions, carbon dioxide was measured to have an effusion rate of 15 milliliters per minute. What would be the rate of effusion for helium at the same conditions?